Guys, can you guys hear me? Can you guys hear me? Okay, perfect. So let's get started. So welcome guys. Welcome to our 2022 AMC10-AIME bootcamp. So the purpose of having this open course is try to give you guys a little bit idea how you can guys do the preparation for the upcoming 2022 AMC10. Hopefully you can do a good preparation and you'll be qualified for the upcoming AIME exam. So basically, the purpose of our lecture is trying to give you guys as much information as possible and give you guys a preparation for the upcoming exam. So before we get started, we just want to give you guys a quick overview what we're going to cover in our 10 lecture. This is actually lecture number 1. We're going to have like 10 lectures in total. So talking about the AMC10/AIME upcoming math competition, we're generally talking about 4 major categories, which is geometry, algebra, counting probabilities, and also number theory. And our 10 lecture was actually basically organized in such a way to make sure we can cover every important point in the upcoming AMC10 math competition. So as a quick overview, what's going to happen is that we're going to use 3 lectures talking about all the geometry part. You know, the geometry, we have like the 2D geometry, which is the foundation, the most important part, talking about the geometry. We have the 3D geometry. So 3D geometry, to be honest, in North American math competition, all the 3D geometry problems, they can be easily converted into a 2D geometry problem. So that being said, as long as you see any 3D geometry problem, your first direction is try to do a conversion. Convert all the 3D problems into a 2D problem, and hopefully taking from there, you got a problem solved. So this is like a big direction I want you guys to take it as a guideline. Do not really stuck with the 3D thing. Try to convert it into the 2D thing. Okay? And then moving forward, we're going to go to our coordinate geometry. So coordinate geometry, we can take it as a liaison between the pure geometry and also the algebra, because the coordinate geometry is just a specific topic. We want to use the algebra way, the algebra tools, technologies, methodologies, whatever, try to solve the geometry problem. So that being said, as long as you're trying to learn the coordinate geometry, you're kind of like 50% in geometry, but 50% is already going to the algebra. We're going to teach you guys different tools, different like theorems, properties, so on and so forth, how to efficiently using the algebra tool to solve the geometry problem. So this is going to be our first 3 lectures talking about geometry. And then moving forward, we're going to use another 3 lectures talking about algebra. You know, algebra is actually what we learned from day 1, right? We learned algebra for a long time. So algebra is a little bit like, what should I say, complex. It's not really complicated, but a little bit complex because there are many concepts. You can't really consolidate them into 1 or 2 topics. So on the contrary, it's actually all over the places. So that being said, we're trying to break our lectures into 3 different sessions and try to cover as many algebra concepts, algebra topics as possible that you will probably going to see in the upcoming math competition. So we're going to cover the functions, the equations, the inequalities, and then we're going to talk about the sequence and series, which is very important. We're going to talk about the exponents. Exponents is more like a lot of flowery problem, interesting problem can be created from the exponents. And then we're going to talk about some functions, advanced functions. We're going to talk something about the trigonometry and polynomial. So generally speaking, in the AMC10 territory, they won't test you too complicated trigonometry and polynomial, for sure not. It's more like for AMC12. But from time to time, they might test you some little things for the geometry from polynomial. If you do not have a very good preparation, you feel like unfamiliar with the topic, you might lose some points. So that's the reason we like to give you guys a little bit exposure, maybe some extra exposure for the trigonometry, polynomial. Make sure you'll be well prepared as long as you basically see all those problems. And then moving forward, as long as we go to our section number 3, we're going to talk about the counting and the probabilities. So generally speaking, counting and probability, these are 2 very similar topics, right? They're basically using the similar technology to try to solve the similar problems. well, still they have some kind of like a specific features in counting and specific features in probability. So that's the reason we break it into 2 lectures. And then the last but not least one is going to be our number theory. Because we have to say number theory is one of the, we'll say, most unfamiliar topic for most of the students, right? Because we learn the algebra, we learn the geometry, we learn the counting skills in our day school. But most of the students do not have a lot of exposure for the number theory, which 100% no problem, because this is actually pretty much all the students they're facing. So such as kind of like a dilemma. However, if you want to take our math competition, especially AMC10, AMC12, AIME, they're going to really ask a lot of knowledge for the number theory part. So that being said, we're going to use 2 lectures, try to give you guys the most important concepts and theorems you need to know in the number theory part, and try to help you guys bridge the gap. And moving forward, help you guys do a good job in the upcoming math competition. Right? This is basically a quick kind of like an overview, the syllabus, what we'll be covering for the upcoming 10 lectures. Well, basically how our lecture is organized. So we're not really just go for problems. I know some lectures just go for problems. I believe it's really inefficient, because basically you see you can do a million problem, but as long as you do a million, you might see a million plus 1 problem in a real math competition. You still get confused. So instead of giving you guys all the problems one after another, we like to help you guys do some summary. So generally speaking, every single lecture is going to be divided into 3 major sections. Section 1 is going to be the concepts. We're going to be covering the most important concepts in AMC, 10, or AIME, so on and so forth, talking about this specific section. So having the concepts already listed out is going to be very important. You know what will be tested, what will not be tested. And then moving forward, the second part, we're going to talk about those important types of questions. You know, there are millions of problems, right? And we can basically classify them into certain categories. I'm going to use the big data analysis to pick up the most important type of questions, give you guys more explanation how this problem looks like, how you're going to use the conditional react and common strategies to try to solve all these problems. And then the last one, we're going to use some real questions. We already talked about the concepts. We classify them into different categories. And our next step is try to give you guys the real problems, how to find some representatives in these different categories and help you guys know how to do all the problems. So this is basically kind of like a big style how we're going to cover it in our lecture. And one thing I want to point out is that in this entire lecture, I'm going to be talking about something called conditional react. Because a lot of students have this problem in the math competition. They're saying that, hey, Alex, I can do the problem, but the time is so limited. I really can't solve the problem in the limited time. I need more time. Well, I know that is pretty much the problem, because most of the time, when you feel the time is so limited, it's because of that every single problem you need to think from the very beginning. Okay, if everything you need to think from the very beginning, doing all those kind of like analysis from the very beginning, it's going to be very low efficient. So on the contrary, we like to teach you guys some conditional react. It's going to be something very mechanical. As long as you see the word, okay, this is your conditional react. As long as you see this kind of condition, this is your conditional react. So that being said, as long as you see some signal words, some signal conditions, you can automatically list out some conditions or find out some kind of like summaries, so on and so forth. So this is going to be very helpful, help you guys to expedite your calculation process. So that being said, in this entire lecture, I'm going to give you as much conditional react as possible. And hopefully after our 10 lectures, you will be able to collect all those important conditional react. And whenever you go to the math competition, it's going to help you to have a fast react and do the problem as fast as possible. All right, I think this is kind of like a quick overview what our lecture is going to look like and what's going to be covered. And we have a lot of interactions in our lectures. So as long as you have any problems, you can just stop me and then raise your hands or even talk to me, whatever. You find out the most, kind of like the most convenient way you like to have in order to participate in this kind of like interaction process. I do not really like have a monologue for the entire process, but this dialogue is very important. Any question, just let me know. You can always talk to me. You can unmute yourself, or you can type it into the group chat. I'll be monitoring the group chat for the entire meeting. So therefore, if you have any questions, I will be able to pick it up and give you guys the real-time feedback. All right, if so far so good, let's go to our lecture number 1. Today, we're going to go to our first part, 2D geometry. Okay, let's go to our lecture 1, 2D geometry. All right, so as I said, at the very beginning, let's go for the concepts, the most important concept that you have to know in order to go to the AMC10 math competition. In the 2D geometry part, of course, triangle is the most important part, right? Triangle is always considered to be the foundation of this entire 2D geometry. So having a good understanding for the triangle-related topics could be extremely important whenever you go to the AMC, AIME, whatever North American math competition. So first thing first, triangle parts. I think the first important part people are talking about is triangle basics, aka triangle inequalities. As long as you got a triangle, you have 3 sizes, then automatically there's a relationship between the 3 sizes. This is something what you learn from day 1, right? So A plus B greater than C. So any kind of the sum for the 2 sizes will be greater than the third one, right? B plus C greater than A, C plus A greater than B. This is kind of like an intrinsic property, right? It has nothing to do with the shape of the triangle. It works for everything. So some student is going to say, hey, Alex, we have learned something else. Not only the sum for the 2 sizes will be greater than the third one, we also have something like A minus B is lesser than C. B minus C lesser than A, C minus A lesser than B, right? The difference between 2 sizes will be lesser than the third one. But actually, if you do a quick analysis, you can find out, let's say this one is actually A lesser than B plus C. A lesser than B plus C. So this guy, B lesser than A plus C. And the same thing, C lesser than B plus A. So that being said, actually means even though you have 2 sets of inequalities, but they're not totally independent. All the subtraction-related inequalities, it can be easily derived from the sum-related inequalities, right? So that being said means what? Means as long as you want to list out the inequality, you do not have to cover 2 things. As long as you cover the add-related inequalities, you're good to go. There's no need for you to cover the subtraction-related inequalities. Okay? And what about the second part? The second part is also very straightforward. Is basically whenever you have a triangle, the triangle 3 interior angle sum is going to be equals to 180 degrees. This is what you learn from your elementary school, right? These are considered to be the basic stuff when you're talking about the triangles. A student get a question, what does the M in front of the angle mean? It means the measurement of angle A, the measurement of angle B, angle C. So basically it means the 3 angles, adding them together equals to 180. Okay, moving forward, let's go to the second part is the famous Pythagorean theorem. Okay, this part, I think you know that from day 1, right? As long as you have a right triangle, you're going to have A square plus B square equals to C square. This is something what you learn from elementary school. Well, to be honest, what's going to happen is that in the real North American math competition, they will barely give you a condition. Let's say I have a right triangle. I have, let's say this is A, this is B. I'm going to ask you to determine what is the length of the hypotenuse, which is C. Trust me, I never ever see something like this. Well, on the contrary, what's going to happen in the real math competition is that I'm going to give you a triangle. So this triangle happens to have 3 sizes, A, B, C. I'm going to give you the 3 sizes up front. And then I'm going to give you other conditions, so on and so forth. Well, some student might get confused. Okay, I have like 3 sizes, A, B, C. I'm just going to do the calculation, so on and so forth. However, sometimes if you do some quick analysis, you're going to find out the condition that the question gives you is going to automatically have A square plus B square equals to C square. So that being said means what? The condition sometimes giving you the three sizes of a triangle without telling you this is actually a right triangle. You need to use the Pythagorean theorem figuring out, okay, this is actually a right triangle. Even though the question doesn't really tell you upfront, but you need to figure out this is actually a right triangle. And taking from there, you'll be able to use a lot of interesting or unique properties from the right triangle in order to solve the problem. Okay? So that being said, you need to really have this knowledge. So what are the three sizes that can create a right triangle? AKA, we call what are the Pythagorean triples? The three numbers, they can put a squared plus b squared equals to c squared. So this is going to be something very important. So here, I actually list out some of the most popular Pythagorean triples, and some of them I need to give you a highlight because these numbers has been tested in our previous AMC math competition. So these are 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, and also the other one is 20, 21, 29. So these numbers are actually based on our analysis. We go through all the problems in the last 20 years. We find out these 4, 5 sets are very important and they test you several times. So that being said, at least you need to be familiar with all those Pythagorean triples. As long as the question gives you three sizes of a triangle, then you kind of have this conditional react, right? Okay, I see these numbers that are like so familiar, so therefore I need to try if they are the three sizes of a right triangle, so on and so forth. So this is actually something very important. Try to remember it. Okay, so let's continue. Angle bisector theorem. Oh, trust me, this is like something so important, and they will be tested almost like every single year. So that being said, as long as you have a angle bisector, okay, so these two angles are the same, right? Angle 1, angle 2. So normally speaking, as long as you see an angle bisector, you're going to have angle 1 equals to angle 2, right? This is quite like understandable. But unfortunately, according to our analysis, we find out AMC barely tests you. If you have an angle bisector, then you have two angles are the same. This is so intuitive. This is like so easy, so naive, but AMC never ever test you. On the contrary, AMC really love to test you is the angle bisector theorem. So as long as you get an angle bisector for this triangle ABC, then automatically you're going to have BD over DC is going to be equal to AB over AC. So this is actually a side relationship, right? Angle bisector is kind of like an angle thing, right? You cut an angle into equally two parts. However, this angle bisector theorem is really going to help you to convert from this angle-related condition into a side-related condition. So this is actually the beauty of the angle bisector theorem. And actually, that's the reason why it really attracts a lot of AMC attentions. So they would like to test you from time to time. So trust me, in the future, as long as you see the angle bisector, your first reaction is always going to be this angle bisector theorem rather than this two angles are the same. We'll be giving you guys some sample problems today that you'll be able to see the beauty of using the angle bisector theorem. All right, if we're good, let's continue. The number 4th part, centers of a triangle. You know, the triangle actually has so many centers, right? If you go to Google, you can find out almost like 100 different centers. But for our high school math competition, there are 4 very important centers that you need to know because they're going to test you from time to time. The first one is, which is the most important, is the centroid. Centroid is actually the 3 medians, right? 3 medians of the triangle will be basically meet at one center C, which is the centroid. Centroid has a lot of specific properties. And you know what? These specific properties can even differentiate from the other centers. Even we're going to do some specific discussion for the properties of the centroid in the triangle in our next part. So for now, we can just skip it. The second part is the in-center. In-center is actually 3 angle bisectors. It's going to be focusing together, concurrent together at the I point. So this point is actually called the incenter. Incenter is the center of the inscribed circle, right? Okay, the other one is the circumcenter. Circumcenter is basically the center of the circumcircle, and how you can basically create it is actually the perpendicular bisector for the three sizes. They will be meeting together at a point, right? So this point is going to be the center of the circumcircle. Okay. The other one is the orthocenter. Orthocenter is not super important, especially for our AMC level. If you go to a higher level, you're going to see there are a lot of crazy properties for the orthocenter. But for us, it's not super important. It's basically three latitudes of the triangle. It's going to be able to meet at a point. That is our orthocenter. So like I said, there are way more centers in the triangle, but for our high school math competition, these 4 centers is pretty much good enough. And on top of this 3, on top of this 4, actually the centroid is the most important. There's a lot of like interesting properties for the centroid rather than the other centers for the AMC10 math competition. What they are? So let's go to our section number 5. Properties of the centroid of triangles. The first important property is that the 3 medians, cut them together, right? The basic go to the centroid. The centroid is going to divide the medians into 2-to-1 portion. So that being said, let's say my G point, right? This is actually my centroid. So it cut this median into 2-to-1 part. Okay? It cut this median also into 2-to-1 part. And the same thing, it cut this median also into 2-to-1 part. So that being said, as long as I see a median, okay, that one you have a centroid in the median, then you can automatically cut the median into 2-to-1 part. This is actually a very important property. And to be honest, there are so many AMC exams. As long as you know this property, the problem can be solved very quick. Okay, that's the first important thing. Well, the second thing is that this is more for the coordinate geometry, but first, for the sake of being complete, I put it here. You know, sometimes whenever I give you a triangle in the XY coordinate, and you have the XY, X1, Y1, X2, Y2, X3, Y3, right? You have the coordinates for the 3 different points, okay? As long as you have the 3 coordinates of 3 different vertices, then you can automatically determine the coordinate of the centroid. Okay, how you can do this? There's something so easy. So the x coordinate of the centroid is just like an average, the arithmetic mean, right? For the x1, x2, x3. And the same thing applies for the y coordinate. Okay, this is actually a very important property, and it can really help you to expedite the calculation process, and you can get the coordinate of centroid very fast. So try to remember this. This is actually something very important. So a student asked me, do I have to remember name of all the centroid or just knowing how they look like? You do not really have to remember the names if you're really asking me, because most of the time, the AMC exam is going to give you the definition. Okay, the AMC will never say, okay, I have a centroid and then blah, blah, blah. So on the contrary, the AMC will say, okay, I have a triangle. The 3 medians is going to meet together at a point. We call it centroid. So if you really can't remember the name, it doesn't matter. But I think it will be easier for you to remember the name. Because sometimes we're not only asking you to remember the name, we're still going to ask you to remember the properties. So here's kind of like a balance. The more formula you remember, the faster you can do the calculation, and vice versa. If you know very little formula, but you are very strong in the calculation, the derivation process, of course, you can do that. But you're going to take a longer time in the derivation process. At the end of the day, that's going to slow down your entire calculation process. So hopefully I answered your question. Yeah, the same thing. If you have any questions, post it in the group chat. I will be able to view it and then give you the answer. All right, so let's continue. Congruent triangles. I think this is actually something very important that we have learned at pretty much in the early phase of our geometry. Congruent triangle means 2 triangles that are exactly the same. They're a copy of each other, right? So how to determine different triangles that are congruent to each other? There are some rules. The first one is SSS. 3 sizes of the two triangles that are exactly the same. Of course, these two triangles will be considered as congruent. 2 sizes and their included angle, right? If 2 triangles, this side, this guy is same, this guy is same, and also their included angles are the same. Of course, these 2 triangles are still congruent to each other. Moving forward, what about you have 2 angles and their included side? Exactly the same thing. So these 2 triangles, you have these 2 yellow angles are the same. These 2 red angles are the same. And also you have this included side. Then you can also determine, okay, these 2 triangles are congruent to each other. Similarly, you have the angle side. You have 2 angles, the same, and another angles opposite side are the same. So you can also determine 2 triangles that are congruent to each other. These are something so familiar, right? You should learn that in your early stage of your geometry. And also for this specific right triangle, we call something, we have RHS, or we call it HL. So what is that? As long as for 2 right triangles, as long as you have 2 legs are the same, and hypotenuse are the same, then automatically you have these 2 right triangles are congruent to each other. This is very understandable because in the right triangle, you have the Pythagorean theorem, right? As long as the yellow are the same, the blue are the same, using the Pythagorean theorem, of course, the 2 greens are the same. This is something so easy, right? So that being said, you will be able to determine 2 right triangles. They are congruent to each other just using 2 conditions. There's no need for you to use, extra condition. A leg and also hypotenuse are the same. They're good enough. Well, I think most of the students, they should ask for the same question is why SSA is not a sufficient condition to prove 2 triangles that are congruent to each other, right? I think when you're learning the congruency, teacher is going to give you the explanation. If you only have 2 sizes and 1 opposite angle of the side, okay, you can't really prove these 2 triangles are congruent to each other. And the reason is, let's say I have this, let me change a different color. This green is the same as this green, no problem. And you have this black angle are the same. Well, the third one is actually the yellow one, right? Well, actually, when you try to create a graph, you see, from here, I use it as the center, and then I can make 2 yellow lines. And both of them have the same length, in our case, let's say 6. So that being said, if you want to have this SSA, you're actually looking at 2 triangles. One is this big red triangle, and the other one is this little black triangle, right? So that being said, these 2 triangles, they both have the SSA, 2 sizes, and also 1 side opposite angle. So that being said, this is not a strong condition enough for you to prove these 2 triangles are congruent to each other. Of course, one of them, the red one, is congruent to the left-hand side, right? But the black one is not. So that being said, that's the reason why when we do the analysis, we exclude SSA, try to be a determination rule of 2 triangles that are congruent to each other. Okay, so this is a quick summary about most important properties for the congruency. Okay, even though congruency is like so important, but to be honest, in our North American math competition, they barely test you too much for the congruency. Why? Because congruency is actually a very strong condition. You need to have 2 triangles exactly the same. Every single point is exactly the same to claim these 2 triangles are actually congruent to each other. Well, in the reality, this is not going to happen. This is going to be too challenging, right? You have 2 triangles. They might not be exactly the same, but they might be very alike, aka they might be similar to each other. Actually, similar triangle is way more important compared with the congruent triangle. A lot of interesting properties were actually derived from the similar triangle rather than the congruent triangle. Having a good understanding for the similar triangle is way more important compared to the congruency. So how to determine two triangles that are similar to each other? We're going to have something similar. The first one is angle, angle. As long as you have two triangles, their two angles are correspondingly equal to each other. Okay, so these two triangles are similar to each other, which makes sense, right? Two angles, good enough. Side, angle, side. As long as you have two triangles, their two sizes, they are proportional to each other. And also you have their included angles are the same, then you can automatically claim these two triangles are similar to each other. Also, side, side, side. As long as you have two triangles, there are three sizes, they're proportional to each other, then you can claim these two triangles are actually similar to each other. You see, these are a lot of very interesting properties for the similarity. If you do a quick comparison, you're going to find out why you have way more congruence. You know, for the congruency, you have way more determination rules rather than the similar. For instance, you do not have the, I'm going to give you one example, ASA, right? In congruency, you have two angles and their included side. Okay, these two triangles will be congruent to each other. You have the AAS, right? You have two angles and one of the opposite side of the angle. You can still make sure these two triangles are congruent to each other. But in our similarity, we do not have all those rules. Why? The reason is easy, because these two things, they can be all consolidated into the angle. As long as you have two angles are the same, I don't really care about our side, right? Your side can be whatever. As long as two angles are the same, it's good enough for us to claim these two triangles are similar to each other. This is actually something so understandable, right? So that being said, if we do a quick comparison between the congruency and the similarity, you can find out for two triangles that are congruent to each other, at least you need to have a side information. You can have three sizes, two sizes, I don't really care, but at least you need to have a side information. However, for similarity, it's not really compulsory. You can only have angle information, and it is good enough for you to determine two triangles that are similar to each other. But if you want to have side information, totally no problem, but side information is not obligation to determine two triangles that are similar to each other. Angle is good enough. All right? So let's continue. Okay, this part is extremely important. Sine law and cosine law, because you're going to see this problem every single year. They're going to test you in AMC, in AIME, even our Canadian math competition is going to test them every single time. So what is the sine law? What is cosine law? For any given triangle, these are all for any given triangle. It has nothing specific to any type of triangle, so on and so forth. You're going to have A over sine A equals to B over sine B equals to C over sine C equals to 2R. So what does this 2R come from? R is the radius of the circumcircle, right? R is the radius of the circumcircle. So this is actually a very important relationship. Tells you the relationship between the side and also a sine value for this opposite angle. This is our famous sine law. The second part is actually way more important. This is the cosine law. So trust me, there's so many math competitions that they just want to test you the cosine law. So having a good understanding for the cosine law is extremely important. So for the cosine law, I think you guys already know this, is basically, let's say, c squared equals to a squared plus b squared minus 2ab cosine c. So think about it. The cosine law is actually a specific tool which will help you to determine the angle relationship just using side. Let's say in our case, cosine c equals a squared b squared minus c squared 2ab, right? This is the cosine c value. You can see on the right-hand side, you only have side. There's no angle information. It's only side. While on the left-hand side, it's only angle. So that being said, it's a very nice rule. Basically segregate the angle and also the side. All the information you have side you have on side, they can solely be used and derive the value of the angle. So if the problem only give you some side and you need to determine some angle information, cosine law is the only law that can help you do such a calculation. So have a look at here. You see in sine law, A over sine A, you need to have the side, you need to have the angle, right? B over sine B, so on and so forth. However, in our cosine law, on the left-hand side is only angle, on the right-hand side is only side. So you can use the only side information to determine the angle information. This is the powerful part of the cosine law. Like I said, there's so many questions testing your cosine law. Having a good understanding for the cosine law is extremely important. All right. Okay, so let's continue. Yeah, now we're pretty much done for all those triangle-related properties. It's time for us to move one step forward. Let's talk about the quadrilateral and the polygon. So quadrilateral, if there's like a general quadrilateral, there's not too much to say. Let's say if the question gives you a general quadrilateral, there's no specific shape, specific condition. Okay, what are you going to do? Your golden rule is always convert a quadrilateral into triangles. Okay, if the question gives you a just kind of a regular quadrilateral, no specific properties, always try to cut it into different triangles, because you have all those kind of properties you have learned, try to do the triangle problems, but you won't have too much interesting or powerful tools you can deal with the quadrilateral. Always do a conversion. Okay, this is something very, very important. You can take it as a conditional react. Okay. But what if you have some specific quadrilaterals? Let's say you have a trapezoid. So if you want to determine the area of a trapezoid, there's no need for you to cut it into two triangles, right? You can basically use A, B, H, right? 1/2 H times top plus bottom, right? That's the way how you determine the area of a trapezoid. Similarly, if you have parallelogram, so in that case, you have A, you have H, so the area can be basically the bottom times the height, right? These are something so understandable. So the same thing applies for the square and rectangle. You know how to do it. So what I'm trying to say, only for some specific trapezoid, specific quadrilateral, you have a certain formula. But most of the general, most of like the non-specific quadrilaterals, you have to break it into different triangles and help you guys solve the problem. And then there's another two parts. This is more like for calculation, is how you're going to determine the angles and the diagonals for any given polygon. If I have any given polygon, whatever, right? I have n is the side. So I would be able to determine the total interior angle sum, which is 180 degrees times n minus 2, right? Because for our triangle, n equals to 3, and the total internal angle sum is going to be 180 degrees, which is kind of harmonic with this specific condition, right? This is more like a generic formula that works for all these polygons. And the same thing, if I want you to determine the diagonals for the polygon, there's also a specific condition, n times n minus 3 divided by 2. You can use such a formula to determine how many diagonals for any given pentagons. Any given polygons. Can be pentagon, hexagon, whatever, octagon, whatever gons, you'll be able to use this formula to determine the total number of the diagonals. All right, I think these are something quite understandable. So moving forward, after we're done for all those triangle, quadrilateral, polygon, it's time to go for the circle. Right? The circle is always the most important part for our geometry because it's kind of consolidate all those interesting properties from the triangle, from this polygon, so on and so forth, and then put it into a more advanced way. So for the circle, of course, you can know some basic stuff, how to determine the area of a circle, how to determine the circumference of a circle, right? These are something quite understandable. And in AMC exam, power of a point is actually something very, very important, and they like to test you from year to year. So when we're talking about the power of a point, you know, this is actually a series of theorems. It's not only one theorem, it's actually 3 different theorems. So the first one is actually the chord theorem, right? As long as you got a circle, you have two chords intersecting each other, then automatically you have AE times EC equals to BE times DE, right? So these two chords is actually cutting them each other, then you can have this part times this part equals to this part times this part, which is quite understandable. Second part is actually what we call a tangent secant theorem. As long as you got a circle, you got a point which is outside the circle. From the point, you want to make a tangent and also a secant to this circle, then automatically you have BA squared equals to BC times BD, right? So this part, perfect square equals to this part times this part. So this is the famous secant, like tangent secant theorem. And also the same thing is, as long as you have two secants, okay, from a point which is outside the circle, you want to make two secants. So you're going to have here times here equals to time here times here. CB times AC equals to CD times CE, right? And actually, you can find out these two formulas are actually the same thing, right? Because as long as you're, let's say, I'm going to have this guy, right? As long as my specific secant is getting closer, closer, closer to the side of the circle, and one day it deteriorates from a secant go to a tangent, right? So by the time the CB and CA, they will be degraded into one single segment. In our case, E. Maybe I'll change a different notation, maybe F, okay? So by the time then, these two things will be degraded into CF squared, right? So that means that the tangent secant theorem and also the secant theorem, they're basically talking about the same thing. Okay, so here, there's actually a very important conditional react I have to highlight for you guys. You know, in the math competition, from time to time, you're going to see different tangent. So what are you going to do as long as you see a tangent? So a student got a question, why it is called power of a point? Okay, that's a special name for such a theorem. So you have this point. So whenever this point is inside the circle, whenever this point is outside the circle, or whenever this point is getting closer to the circle, you have different properties. So we give a name, power of a point. It's kind of like a name. It's kind of like the name. You know, sometimes why they call it Pythagorean? Because Pythagorean find out the theorem. Sometimes they just find a fancy name for the specific theorem. Okay, so let's continue. What should you do whenever you see a tangent? This is actually something important because in a math competition, you're always going to see some tangent condition. What are you going to do? What is our conditional react as long as you see the tangent condition? So there are several very important conditional react. First one first. As long as you see a circle and you see a tangent line, which is tangent to the circle, then automatically you want to make a connection from the circle center to the tangent foot. Because as long as you make this connection, you will find out a perpendicular, right? Because the connection between the circle center to the tangent foot is going to be perpendicular for this tangent line, right? This is actually so important. This is like so easy. However, this is going to be so important. From the circle center to a connection, make a connection to the tangent foot. Because this is going to generate a perpendicular line. Okay, this is more like whenever you have a line and you have a circle. Second part is, as long as you see two circles that are tangent to each other, what are you going to do? So let's say whenever you have two circles, they are externally tangent. Okay? Or you have two circles, they are externally tangent, right? One is internal, one is external. So always, what you're going to do is try to make the connection between two circle centers. Connection between two circle centers. Okay? Make the connection between two circle centers. Because as long as you do the connection, you can find out when you have two circles, they are externally tangent to each other. The two circle centers and this tangent point, they will be collinear. Okay, they're basically on the same line. And similarly, whenever you have two circles, they're internally tangent to each other. When you do the connection, of course, the tangent foot is not on the segment. However, if you try to extend this segment, you can find out the tangent foot is also on this extension of this segment. So also you see a collinear. Okay, so that being said, whenever you have two circles, they're tangent to each other, always do the connection between these two circle centers because you're going to see a collinear from the two circle centers and also the tangent foot. Of course, another quick thing you can find out, let's say if I call this is big R, this is small r, the distance between these two circle centers will be big R plus small r, right? And in our case, the distance is going to be big R minus small r, right? This is something quite understandable. Okay, and these are two very important things you need to remember. And there's a third one, which is even more important. I really want you guys to remember because many AMC problems just test this property directly. Whenever you have two circles, they're externally tangent to each other. And on top of that, you have another common tangent line. All right, this common tangent line cuts these two circles. Okay, it doesn't matter, right? Because these two circles have two tangent lines. In that case, okay, I'm going to tell you what is the conditional react. So what you're going to do is, first thing first, as long as you see two circles that are tangent to each other, I told you guys, try to do a connection between the two circle centers, right? This is exactly according to what we just mentioned. And second, we mentioned, as long as you have a line tangent to a circle, you're going to try to do a connection between the circle center and the tangent foot, right? Because you're going to automatically generate a perpendicular line. Well, the third step is very important. You can try to do a perpendicular line from the relatively smaller circle center to the big circle's radius. Okay, let's try to do a perpendicular line to here. And most of the magic is going to happen in this little red triangle. So let's have a look at it. What's going to happen? Let's say I have this big triangle. It has a radius r. Small circle has a radius small r, for instance. Of course, we know the distance between these two circle centers will be big R plus small r, right? And also, because I made a perpendicular line from the small triangle, from the small circle to the big circle, if this is R, so this is going to be R as well, right? It's a rectangle. So therefore, here, you're going to have big R minus small r. Is that right? Which is quite understandable. So that being said, if I drag out this right triangle, this is big R minus small r. This is big R plus small r. So here is going to be 2 under root big R times small r, right? You can using the Pythagorean theorem, right? Using R plus R perfect square minus R perfect square, take an under root. That's going to be the value for this third line, right? And what is that? That is actually the distance between these two tangent foot, right? The distance between these two tangent foot. You know what? Trust me, in many AMC competition, they just basically use such a property. It's like so easy as long as you know such little right triangle is going to help you to expedite your calculation significantly. In today's sample exam, I'm going to give you some problems and you can find out as long as you remember this is something so easy. Okay, this is our second conditional react. Our third conditional react is also very understandable. As long as you see a circle, as long as you see there's a chord on the circle, so try to do a perpendicular line from the circle center to the chord. Perpendicular line from O to the chord. Why? Because as long as you make a perpendicular line, you can automatically cut this chord into two parts, two equal parts. Is that right? Because if you do a connection, this is going to be what? This is going to be an isosceles triangle. Isosceles triangle, if you see a height, the height is also a median, right? So this is actually something very understandable, but also very important. It's considered to be a very good conditional react. As long as you see a chord, try to make a perpendicular line from the center of the circle to the chord, and you'll be able to see you're going to cut the chord into two equal parts. So far, so good? So let's continue. Okay, so in the circle part, we actually got a specific type of quadrilateral. We call it cyclic quadrilateral. Cyclic quadrilateral means this quadrilateral, the four vertices is actually on the same circle. Okay, as long as you have such a cyclic quadrilateral, so you have some special properties. The first property is that for any given cyclic quadrilateral, the opposite two angles, they are supplementary to each other. So these two blue ones adding them together equals to 180 degrees. Same thing, these two guys, the two green ones adding them together, you see 180 degrees. So this is actually a very important property for a cyclic quadrilateral. And trust me, this is a necessary and sufficient condition. So that being said, as long as you have a quadrilateral, you have these two sizes, right? These two guys, so adding them together equals to 180 degrees. You can say this is a cyclic quadrilateral. And also, as long as the question gives you a cyclic quadrilateral, you can claim the opposite two angles will be supplement. This is actually something very important. Especially, sometimes when the question gives you something like this, because AMC love to test you something like this. When I give you a kind of a quadrilateral, okay? And I say this quadrilateral has these two angles equals to 90 degrees. Of course, these two opposite angles, adding them together, basically give you 180 degrees. So that one, automatically, you can say this is going to be a cyclic quadrilateral. Trust me, this is a very important property, and using this property is going to help you a lot when you're trying to deal with a lot of problems. Later, I'm going to show you AIME problem. If you use such a property, it's going to help you to save your time, solve the problem in about maybe 30 seconds. Very easy. Okay, so our lecture have already explained for the quadrilateral, our regular lecture spent a lot of efforts talking about the cyclic quadrilateral. So in today's lecture, it's only like a quick overview, so we won't be able to go for super in detail. If you need more information, you can contact me offline. I'll be able to provide some extra information. Okay? And as long as I give you a quadrilateral, let's say, okay, any kind of random quadrilateral, of course, there's no way for you to determine the area of it, right? The only thing you can do is try to cut it into two triangles, and hopefully you'll get an answer from a triangle. However, if the quadrilateral I'm giving you is not a regular quadrilateral, it's a cyclic quadrilateral, so you will be able to determine the area fairly quick. So this is the formula we're talking about, okay? As long as I got quadrilateral, they have A, B, C, D, four sizes, okay? Then I would be able to determine the area of this quadrilateral simply by using such a formula. I'm going to determine S equals to A, B, C, D, adding them together, divided by 2. And then the total area of this quadrilateral is going to be under root S minus A, S minus B, minus C, minus D. This is more like the Heron's formula, right? Heron's formula is more like for the triangle, but this is for the quadrilateral, right? So this is actually something very interesting. But not all the quadrilaterals you can do such a way to determine the area. It has to be a cyclic quadrilateral, and you can use such a way to determine the area. Okay, so let's continue. Number 12, the famous Ptolemy theorem. As long as you got a quadrilateral, this is a cyclic quadrilateral, then automatically there are some relationship between all the sizes. So the relationship is, if you take, I'm going to change the color to here. If you take the sum of the product of this two opposite sides, the sum of the product of the two opposite sides will be equal to the product of these two diagonals. In our case, AC times BD, two diagonals, it will be equals to AB times CD plus BC times AD. I use the same color from the formula and also to the graph, right? You'll be able to see, okay, the two yellow parts, multiple them together will be equal to the two, basically the two green part and the two yellow and the two red parts. They multiple them together and adding them together. This is actually a very important property for our cyclic quadrilateral. Okay, and also we would be able to use such a property, try to solve a lot of interesting problems from the AMC. Later, I'm going to show you there are a lot of interesting problems. They can be quickly solved using the Ptolemy theorem of a given cyclic quadrilateral. Okay, so that's pretty much what I want to say for the circle part. Okay, before we wrap up our concepts part, I want to talk a very, very important property, what we call the area of a triangle. So trust me, the triangle actually, we have different triangles. From time to time, want to determine the area of a triangle. So trust me, there are many ways to determine the area of a triangle. If you do a quick analysis for all the the AMC, AMC10 related, geometry related problem in the last 20 years, you're going to find out there are 80% of the problem. They're somehow talking about the area of a triangle. 80% of the older geometry problem, they're kind of like using somewhat have some connection for the area of a triangle. So that being said, having a good understanding for how to determine the area of a triangle is going to be something extremely important. All right, with all of this, let's have a look at it. How are we going to determine the area of a triangle and how many different ways we can determine the area of a triangle? Okay, first thing first, using the definition. This is something you learn from elementary school, right? You have a triangle, you have a bottom, and you have a height. So the triangle's area is 1 or 2, bottom times height. Period. So easy. Section number 2 is the famous Heron's formula. I think you guys should know this Heron's formula in different kind of math competitions. As long as you have a triangle, any kind of triangle, there's no need to be a specific triangle, obtuse triangle, or acute triangle, no. Any kind of triangle. As long as you have the 3 sizes of the triangle given, then you will be able to determine the area of the triangle simply by using such a formula. S times S minus A, S minus B, S minus C, and then I take an under root. Okay, and what's the value of S? S is A plus B plus C divided by 2. Okay, if you do a quick comparison between here and something we talk about here, you see, whenever you have a cyclic quadrilateral, aka a quadrilateral, you can insert it into a circle. So you will be able to see, look, the area looks like this. S minus A minus B all the way to minus D. And S is actually A plus B plus C plus D divided by 2. Right? This is for cyclic. And if you go to our triangle, all the triangle must have a circumcircle, right? If I give you a quadrilateral, there's no guarantee, right? This quadrilateral must be a cyclic quadrilateral, but if any kind of triangle must be a cyclic triangle, right? There must be a way for you to find a circle to make sure the 3 vertices of a triangle stays on the circle. So as long as a shape, they can be inserted into a circle, you would be able to calculate the area of the shape simply using something like S is all the sides, adding them together, divided by 2, and then the area is under root S times X minus the first side x minus the second side, all the way s minus to the last side. Can you see that? So that being said, the Heron's formula and also our previous, quadrilaterals, cyclic quadrilaterals area, this is actually something very understandable. Okay, so some student says, how can you use the formula with any cyclic polygon? Of course, this is going to be applicable for all the cyclic, not quadrilaterals. It's going to be any polygons, right? As long as I got a polygon, I think that's a very good question. I got a polygon. So this polygon is a cyclic. I don't know, any kind of polygons. A, B, C, D, E, F. As long as you have such a polygon, you can always define an S. S is adding everything together divided by 2. And the area will be S, S minus A, S minus B, all the way S minus whatever. As long as you have a cyclic polygon, you'll be able to use such a formula to determine the area. That's actually a very interesting observation. In our math competition courses, we always want to ask you guys to start with something easy, a triangle or maybe a quadrilateral, and then get the pattern from there and moving forward, try to solve all the problems. This is actually something very important. Okay? But to be honest, in the North American math competition, they barely test you polygon, right? They basically test you the quadrilateral, the cyclic quadrilateral is good enough. Okay, so let's continue. We finish up the second one, Heron's formula. And then the other one is the trigonometry. We can always determine a triangle's area using 1/2 AB sine C. A, B are the two sizes. C is the included angle. So you will be able to determine the area of a triangle using two sides, multiply them together, and also the sinus value of this included angle. Okay? And moving forward, there are two formulas which you might not be very familiar with, but trust me, they're extremely important. As long as you know this, sometimes it's going to help you to expedite your calculation significantly. The first one is, whenever I have a triangle and I have a inscribed circle, okay, inscribed circle, okay, R is the radius of the inscribed circle. So the area of the triangle must be able to be written as R times S. R is the radius of the inscribed circle. S is the half of the perimeter of the triangle. A plus B plus C, okay, this is the perimeter, half of the perimeter times the radius of the inscribed circle, you will be able to determine the area of the triangle. This is something very important. If you know this, it's going to help you to expedite your calculation significantly. And this is our number one. What about number two? Number two is not talking about the inscribed circle, but it's talking about the circumcircle. You see, all those interesting properties, they come in pair. Like the inscribed circle, circumcircle. If you have a triangle ABC, like I said, all the triangle must have a circumcircle, right? And you have a R as the radius of the circumcircle. So the area of this triangle will be written as ABC, three sizes, multiply them together, over 4R. Okay, over 4 times the radius of the circumcircle. So we have already given you guys an explanation how you're going to prove this in our regular lecture. So this is a bootcamp, so we don't really want to waste the time to do a full proving process, but try to remember this too. So these two is going to be very important, and it's going to help you a lot in the North American math competition, especially for AMC10, AIME, so on and so forth. That's going to help you a lot in the process. So far, so good? Okay, let's continue. This is actually number 1, 2, 3, 4. Okay, let's go to number 5. Using the similarity, you can also try to determine triangle's area. So let's say I have 2 triangles, they're similar to each other. So if two triangles, they're similar to each other, the area ratio of two similar triangles, area ratio of these two similar triangles will be the perfect sum, perfect square of the similarities ratio, right? Areas ratio is going to be the similarities ratio's perfect square. So let's say, I'll give an example. If this is A, oops, if this is A, this is A prime. So triangle ABC area, triangle A prime, B prime, C prime area is going to be A over A prime, make a perfect square. Oh, this is like so important. This guy is going to be tested all over the places, especially, you know, in AMC12, AIME, a lot of complicated problems can be easily solved as long as you use such a conclusion. This is also something very understandable, right? Moving forward, the last thing I want to say is, you know what? If the question asks you to determine the area of an equilateral triangle, you need to remember such a formula. You don't really have to do the calculation from the very beginning. So as long as you get an equilateral triangle, if the three sizes are A, so the height will be under root 3 over 2A. And the total area will be under root 3 over 4A squared. So this is also, you know, this is not a super important property, but I think most of the students know it and they can use it to expedite your calculation process. All right, I think that's pretty much what I want to say for all the important concepts that you need to know in order to go to the AMC10 exam. This is actually our section number 1. Try to cover all those important concepts. Okay, so you have any questions? All good? Okay, perfect. So if all good, let's go to our second part. Important type of questions. What are the important questions you need to deal with in order? What are the important questions? Type of questions you need to deal with as long as you want to go to this like the 2D geometry part in the AMC related stuff. Okay, student got a question. What is the conditional react for the cyclic quadrilateral? Is Ptolemy or angle chasing? That's a very good question. As long as you see this cyclic quadrilateral, there are many things you need to take it as a conditional react. You need to think about it, the definition. The definition means what is a cyclic quadrilateral? Means there's one point, right? This point has like 4, 1, 2, 3, 4. They have exactly the distance from this one point for these 4 vertices are identical, right? This one point is actually the center. You need to talk about the Ptolemy theorem. You need to talk about all those kind of angle chasing, right? And these are the basic conditional react. In our regular lecture, we actually give you guys a list, everything that you need to remember. But generally speaking, these 3 things are the most important thing. One is the definition. Second one is the opposite 2 angles are supplementary. The third one is Ptolemy. Okay, so this is actually the question. This is basically to answer student question. What are you going to do whenever you see a cyclic quadrilateral? Okay, so let's continue. What are the important types of questions when you're dealing with the 2D geometry part? So generally speaking, I think there are 4 parts you need to basically pay attention to. The first one is the area method. Like I said, if the question might ask you to determine a certain triangle, if not polygons area, so you really need to see a lot of problems basically talking about the area. So having good understanding for all those area-related formulas, and it will be very important for you to determine the area of given shapes. Second part is actually, you know, sometimes try to use some trigonometry. You know, like I said, you guys do not have to remember a lot of complicated trigonometry, especially for AMC10. It's not so important. However, if you can remember some certain numbers trigonometry, it's going to help you to expedite your calculation process. So what I mean when I say certain number, you see, in our regular school, we know the trigonometry for 0 degrees, 30 degrees, 45, 60, 90, right? These are the most popular trigonometry degrees. However, if you can remember a little bit more than this, that's going to help you significantly in a lot of math competition related problems. So let's say if you want to remember some 15-degree related trigonometry, or you want to remember some 36-degree related trigonometry, or something like 72-degree related trigonometry, or something like 75-degree related trigonometry. Trust me, if you remember this specific numbers trigonometry, that's going to help you significantly to expedite your calculation process. Of course, you do not have to, because you can always use a lot of complicated calculation to get a value. But if you do this quick trick, it's going to help you to expedite your calculations significantly. Today, we're going to give you some examples. You will figure out how I can use some certain numbers trigonometry. I can help to expedite the calculation process. Okay. And the third one I want to say is something like the tangent related problem. This is more for the circle. As long as you see circle, tangent with lines, or different circles, they're tangent with each other, there are a lot of certain conditional react. That's going to help you in order to expedite your calculation process. And the last one is some kind of like circle-related theorems, like the power of a point, or Ptolemy theorem. So these are considered to be some advanced theorems. You want to put them together, some combination, try to solve some relatively difficult problem. So generally speaking, these are four major important problems you're looking at whenever you want to go to the AMC 10 math competition. The area method, some specific trigonometries, the tangent-related problem, and the power of a point. Today, we're going to give you guys some sample problems to cover this four category, and hopefully using these sample problems, give you guys an idea how to deal with this relatively classified problems, and you'll be able to expedite your calculation process. All right, if all good, let's go to our section number 3. Try to give you sample problems for these four categories. 3, okay, sample problems. Let's go to our first one. Like I said, area method is actually something so important. Let's go to our question number 1. Question number 1 is a problem that comes from 2017 AMC10B, question number 21. Like I said, our lectures always focus on the relatively difficult problems. We always give you the last 5 problems in the AMC10 exam and some AIME problems. So as a start, I give you 30 seconds, read the problem, and then we're going to do this all together. All right, time is up. Let's try to read the problem together. Okay, let's see how we're going to deal with this problem. In a triangle ABC, okay, I have like ABC, A, B, C. I have AB equals to 6, AC equals to 8, BC equals to 10. Okay, as long as you see a question give you 3 sizes, what are you going to do? You need to think about it. The 3 sizes are given for fun, or there are some certain specific properties for the 3 sizes, right? The 3 sizes is what? 6, 8, 10. It's a what? It's a Pythagorean triple, right? Like I said, in our previous section, the question always want to give you some numbers. There happen to be a right triangle 3 sides, but the question will not directly tell you this is a right triangle. You need to have this eyes to find out this is actually a Pythagorean triple. So that being said, this is what? This is a right triangle. You see, you need to remember this. Pythagorean triple is always they want to test you. Okay, this is when you read a problem, you need to kind of have this conditional react. Okay, and D is the midpoint of BC. Okay, D is the midpoint. And what is the sum of the radi of the circles inscribed in ADB and ADC? Okay, so basically you need to determine these 2 circles. This is R1, this is R2. Okay, so now I know I have a right triangle. And in this right triangle, I have AD. AD is the median of the hypotenuse. Okay, according to our basic knowledge, a right triangle's hypotenuse median, AD, is actually half of the hypotenuse, right? So AD actually equals to 5. These are all conditional react, right? Okay, you know this guy actually equals to 5. Well, the question asks you to determine the radius. How can you determine the radius? Is it something easy for you to determine the radius? Who can tell me what kind of formulas we have introduced so far that can easily help you to determine the radius of an inscribed circle? I'm going to be asking for, yeah, you can post the answers into group chat. So I'm going to have some interaction with all the students, okay? Who can tell me? So I'm going to ask maybe Michael soon.
Is the area is equal to the radius in radius times the semi-perimeter, and know the semi-perimeter and the area is confined. So it's solve the equation to get the radius.
Is that right? That's a brilliant answer. Yes, we just told you that area of a triangle is equal to the radius of the inscribed circle plus the S, right? Maybe I'm going to use this. I'm going to change this area. That's going to be more easy. Okay, the area is actually R times S. S is the semi of the perimeter, right? So that being said, something like so easy. So in our triangle ABD, okay, let's talk about like the red one, triangle ABD, right? So how can I do this? R2 times semi-radius, semi-perimeter. This is 2, 5, 5, 6 equals to the area of this red triangle. What is the area of this red triangle? The red area of this triangle is only half of the right triangle, right? Because this is the median. So therefore, the red one and the big triangle, they share the same height, but it's only half of the bottom. Is that right? So therefore, the area of this triangle ABD is 1/2 of the ABC's right triangle. This is something like so easy, right? So with all this information, you'll be able to determine R2 equals to 3/2. Similarly, you already know how to determine the area for the red one. You can do exactly the same thing to determine R1, right? So R1 is what? R1 is in triangle ADC. ADC. You're going to have R1 times 8 plus 5 plus 5 divided by 2 equals to also triangle ACD. The black triangle's area is also 1/2 of the big triangle ABC, right? So R1 equals to 4/3. That's it. So easy, right? So the question asks you, what's the value for R1 plus R2? You just basically add these two numbers together. That's going to give you 17/6. That's the D part. You see? This is a question number 21, but I think you can just solve the problem in about 1 minute. That's it, including the calculation, including how to read the problem. This is actually something so easy as long as you remember what we introduced in our problem, right? That's actually our question number 1. Okay, so good. Let's go to our question number 2. Okay, they're so easy as long as you know what we introduced in our lecture. They're like so easy to solve all those problems. Question number 2. This is a problem that comes from 2018 AMC10-A, question number 24. Again, 30 seconds. I'll let you guys read the problem first. All right, so let's have a quick look at it. How are we going to deal with such a problem? Triangle ABC, you have AB equals to 50. AB equals to 50. I'm going to highlight it here, okay? AC equals to 10. Okay, the question already gave you this condition. This is like 50. This is like 10. Okay, has an area 120. Okay, the question gives you an area of a triangle. Okay, let's just park it there. Let D be the midpoint of AB. D is the mid. Let E be the midpoint of AC. E is also mid. Okay, you have two mid. Then automatically, okay, as long as you see this, you will see DE is actually parallel to BC. Right? Two midpoint, you make a connection. So the DE segment is going to be parallel to BC. These are all conditional react. As long as you're reading, you need to have all those kind of conditions popping up. I don't know, this is going to be helpful or not helpful. I don't know, but let's just park it there. Let's continue. The angle bisector of BAC intersects DE and BC at F and G. Angle bisector. Still remember, like I said, as long as you see angle bisector, automatically you're going to think about the angle bisector theorem. Is that right? Angle bisector theorem is way more important than two angles are the same. Angle bisector in our case, AB over AC equals to BG over GC. This is an angle bisector for this big triangle ABC. Like I said, I don't know if this is going to be helpful or not, but let's just park it there. Everything is popping up like this. Okay. With all those information, the question is asking you to determine what is the area of FDBG. FDBG is this green one. How to determine the area of a quadrilateral? This is a quadrilateral, right? And you don't really know what kind of specialty for this quadrilateral. It just may be like a random quadrilateral, nothing really special, right? Okay, so if I wanted you to determine a random quadrilateral's area, I think we have already mentioned, using our conditional react, a random quadrilateral's area must be derived using a triangle's area. You won't be able to determine the random quadrilateral's area. You have to determine from a triangle's area. But how can I get this triangle's area? Cutting it? Connect the BF or connect DG? Or I might use some other workaround to find out the area. You know, to answer this question, it might not be on top of my head. Let's try to do some analysis. So this problem already gave me an area, which is 120, which is the big area, like the big triangle, right? ABC's area. I'm going to write it here. Triangle ABC's area equals to 120. Okay. If triangle ABC's area equals to 20, is there any way for me to determine, like the green area? Can I find out a relationship between the green area and also the big triangle's area? I think this is not something too complicated. Let's think about it. If I want to determine the green, I'm going to use the color green, okay? That's going to be easier. Okay. If I want to determine the area of my green quadrilateral, if for some reason I can find out the relationship between this green quadrilateral and this red triangle, because your quadrilateral stays this red triangle, right? This red triangle, ABG. If I can somehow find a relation from it, okay? And from this big red triangle, ABC, I can also find a relationship with this entire triangle, ABG, excuse me, this is ABG. Okay, if I can find some relationship from my green quadrilateral to this red triangle ABG, all the way to this big triangle ABC, because the big triangle ABC's area is already given by the problem, right? If I can find such a relationship, then maybe I'm going to be able to solve the problem fairly quick, right? How can I find out this relationship? Let's do this one by one. Okay, Rome wasn't built in a day. Let's do this step by step. Find out the relationship between the green quadrilateral and this red triangle ABG. This is not something too complicated because we already find there's a condition. DE is parallel to BC. So therefore, my triangle ADF is actually similar to my triangle ABG, right? ADF is this little triangle. ABG is this big red triangle. And the similarity ratio is going to be 1/2, right? Because this is the midpoint. As long as you have such a relationship, using the formula we introduced, two similar triangles' area ratio is their similarity ratio's perfect square. So therefore, my ADF's area over my ABG's area is going to be 1/4. Is that right? Okay. If these two guys, the area ratio is 1/4, then my green quadrilaterals triangle and my ABG's triangle is going to be 3/4, right? The entire thing is 4 part. This is 1 part. This is 3 part. The entire thing is 4 part. So my green quadrilateral is 3/4 of my red ABG, right? This is something quite understandable. Okay, I kind of find out the relationship from ABG, right? From here to here. Now I'm gonna find out a relationship in this two. What's the relationship from my ABG's area and my big ABC's area? That part, who can tell me? I'm going to be asking maybe Li Tong Lo. Can you? Yeah. So I'm going to be asking like some students. If you are okay, you can basically unmute yourself, and then maybe just give us the answer. Do you know how to determine the relationship between ABG and the big area, ABC?
Maybe like first multiply the ratio of ADE to ABC with the ratio of ABG to ABC because it basically intersects.
Okay, yeah. But do you have something more straightforward? If I want to determine this area, I'm just going to highlight it for you, okay? This guy, my black one, okay, this area and big triangle ABC's area, do we have something more direct? You can use one step to figure out the ratio right away.
So then the ratio from BG and GC is 5 to 1.
Exactly, right?
So it's 5/6.
Exactly. This is actually using what? Your angle bisector theorem, right? Like I said, angle bisector is like so important. As long as you see there's an angle bisector, you're going to see BG over GC is the same as AB over AC, which is 5/1. So that being said, your triangle here actually takes 5 portion. This is 1 portion. So your ABG all the way to ABC is actually 5/6 triangle ABC. Is it right? Okay, as long as you know this, the entire process can be so straightforward, right? Because we know triangle ABC's area is 120, and the triangle ABG's area is actually 5/6 triangle ABC's area. This is only 100, right? And then moving forward, your triangle, your quadrilaterals area is 3/4 times triangle ABG area is definitely 35, like 75. So 75, you have the correct answer. That's it. You see, this is a problem question number 24, right? But I think it's very straightforward. As long as you have the understanding about the angle bisector theorem, you'll be able to find out a relationship between them, right? As long as you find out the angle bisector theorem, you just need to find out what we mentioned. As long as the question asks you to determine here, quadrilateral, a random quadrilaterals area, always convert it into a triangles area. The one after another, you will be able to get what you need. One step after another, right? Every single step is very reasonable, very understandable for you to go to the next step. So far, so good? Okay. So these are actually 2 AMC problems. You'll be able to dealing with the area, so on and so forth. Now, let's go for one AIME problem. Okay, I'm going to give you an AIME problem. You're going to find out if you try to use the technology we introduced, it's still very easy for you to get an answer. Let's go for an AIME problem. 1, 3. There you go. This is a problem that comes from 2011, AIME 2, question number 10. Again, 30 seconds. I'll let you guys read the problem first. All right, so let's have a look at it. The question says, a circle with a center O has a radius 25. Okay, the radius is already given to 25. Chord AB has a length 30. Okay, AB has a length 30. Chord CD has a length 14. Okay, you have basically 2 chords. The length is already given. Okay, they intersect as a point P. The distance between the midpoints of the 2 chords is 12. So let's say EF are the 2 midpoints, right? You do a connection between these 2 midpoints. The distance is 12. I'm going to write it here. This is 12. Okay. And the question asks you to connect OP. Okay, I have to connect OP from here. Where's O? Oh, oops. Do an OP connection. Okay. Okay. The question asks you to connect OP. And then the quantity of OP can be represented as m over n, where m and they're relatively prime positive integers. Find out the remainder when m plus n is divided by 1000. This is a typical way that AIME likes to test you. Why? Because AIME, the correct answer for AIME is always an integer from 0 to 999. So that being said, it won't be able to ask you the value for OP. OP might be a fraction number, right? So on the contrary, they like to put OP into m over n, and then m will be m and n, their relatively prime number means what? You just make this fraction number as easy as possible, the simplified fraction number. And then the question might ask you m plus n's value, and then divide something, so on and so forth. So don't be confused. As long as you see such a weird way that AIME like to ask you, it just basically asks you, what's the value for OP square? As long as you know the value of OP, you make a perfect square, you get what you need. Okay, how can I determine the value of OP? This is actually a little bit challenging, right? I need to find out the value for OP, and then taking from there, hopefully I'll be able to get what I need. But you know what? Like I said, it's not so easy to directly jump to OP. We might have to do a little bit preparations, walk around, find out conditional react before we go to where we need to do. So now this problem has a chord, okay? Two chords actually intersect with each other. And then you have the two midpoints of the chords. Do a connection, EF equals to 12. So using the conditional react we have introduced previously, as long as you see a chord, who can tell me what is your conditional react? Still remember? As long as you see a chord, what are you going to do? I'll be asking maybe Olivia Lee. Olivia Lee. No? Okay, no problem. So maybe I'm going to ask like Thomas. You can unmute yourself.
You just draw a perpendicular line from the center O to the center of the chord.
Is that right? That's exactly what we mentioned, right? So I told you guys to draw a perpendicular line, and this perpendicular line will basically the midpoint, right? This chord. The question already gave you the midpoint, E and F. So you basically do a connection, okay? You basically connect OE, connect OF. You're gonna have two perpendicular lines, right? This is something so easy. Okay, do a perpendicular line here, here. Okay. As long as you do a perpendicular line, I think it's very easy for you to determine the value of OE. Is that right? The question already gave you the length of A chord, AB chord, and CD chord. Let's say AB chord is 30, so 1/2 will be 15. The question already tell you what is the radius of the circle, which is 25. So it's very easy for you to determine the value of OE. OE is 20, right? OE using the Pythagorean theorem, 25 square minus 15 square equals to 20. Similarly, OF, 25 square minus 7 square equals to 24. Is that right? So these are easy peasy stuff, right? Nothing. These are based on the conditional react. So now you're kind of doing something like this. You have a, see here, I'm going to change the color. You have a EOFP. Okay. this EOFP, you have two perpendicular lines, right? You have two 90 degrees here. Let's highlight it from here. 90 degrees, 90 degrees. And you know the three sizes of OEF, right? And then you need to determine OP. Do you have something easy to determine OP? You have a triangle. So this triangle actually has three sizes, it's already given. And you kind of have like two perpendicular stuff. I'm not so sure, but that's okay, it's there. And with all of this, you need to determine OP. How to determine OP? I think many students find out a very good observation. I'm going to ask Galan, is there any special for this specific quadrilateral?
It would be cyclic because EF are congruent.
Is it right? That's a brilliant observation. EOFP is cyclic, right? Because the opposite two angles are supplement to each other. Okay, if you have a cyclic quadrilateral, I'm going to write it here, even though I do not really have to write out the circle, but I'm just going to write out the circle. If there's a circle, sorry about my horrible writing, but anyway, you have a circle there, right? Okay. If I write out the circle, if I want to determine the value of OP, I think most of the students, your first reaction is using Ptolemy, which is 100% no problem, right? Because in Ptolemy, you have sizes, you have diagonals. That's pretty much what you're going to do. But if you want to use Ptolemy, you have to determine this guy, right? And you have to determine this guy as well, right? You need to determine the two before you can basically figure out the Ptolemy. But given the condition, you might not be that easy to remember, to basically determine like the yellow one and the green one, right? A student got a question, EPFO is a rectangle? No, they're not rectangle. You only have these two guys, 90 degrees, but you totally have no idea angle P and angle O. It's only my writing looks like rectangle. No, they're totally not a rectangle. At least there's no guaranteed to be rectangle. If that being said, do we have something a lot straightforward and easier for us to get all the angles? I mean, for us to get the solution of OP? Trust me, if you go to the official solution of this problem, it's super complicated. They use a lot of calculation, a lot of similarity, blah, 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 to make it happen. However, if you use my solution, only one step, you get what you need. Let's have a quick look at it. OP. Is the OP segment a little bit special or something? Like OP, in terms of this red circle, what kind of segment this OP is? Jonathan?
The diameter?
That's the diameter, right? Right. If that's the diameter, let's have a look at it about this guy. I'm going to use the color maybe black. I have a triangle here, right? This triangle, I'm going to highlight it using this. This black triangle is basically a triangle inscribed in the circle, right? And this triangle, I'm going to maybe rewrite it here. Right? This is my E, this is my P, F, O. I write this EFO. This EFO is a triangle inscribed in a circle. I already know three sizes of this triangle. This is 20 5. This is 24. The question tells me this is 12. It is very easy for you to determine the area of E or F using Heron's formula. Is it right? Using Heron's formula, this is actually 32 under root 14. Right? You have no problem. You know the 3 sizes, you use in the Heron's formula, you get what you need. Right. If that's the case, let's think about it. We actually introduce a very interesting property. A triangle's area can be written as ABC for R. Still remember? ABC over 4R. 4R is what? This is the circumcircle's radius. Circumcircle's radius. Is it right? ABC. ABC over 4R. Right? So if that's the case, what is 4R? If I remember, if I calculate that value for R, my OP is directly equals to 2R. Is it right? Because my OP is the diameter. Right? The diameter would be so easy for you to determine it actually equals to 2R. So that being said, you see, I got this problem solved so easy. This area is 32 root 14. ABC, I know them already, 25, 24, 12. 4R. It's very easy for me to determine the value for R. R is 45 over root 14. Right? If that's the thing, I'm going to be able to determine OP's value. OP is actually doubled of R value. Is that right? So if the question asks you to determine what's the value for OP square, 4R square. And the value is simply for you, 4050 divided by 7. The question is asking, this is going to be M, this is going to be N. What is M plus N divided 1000? So the remainder is actually 0.57. That's it. So far, so good. You see, this is AIME question number 10. But using my solution is fairly easy, right? You solve the problem in about only 3 formulas. You know this, you get this, and then you use directly this. You get a value for OP. You guys follow me? Can I have some feedbacks? Yes or no? Look, so easy, right? Do not read the official answers. Too complicated, using a lot of weird calculation here and there. But using my way, so easy. So that's the reason you have to know such a formula. If you know such a formula, it will be so easy for you to determine your area right away. Okay? So a bunch of students got some questions. Why OP is the diameter? Why OP is the diameter is because this guy is 90 degrees. The chord which is facing a 90-degree angle will be the diameter, right? That's a basic circle property. A chord facing a 90-degree diameter will be like the diameter. What is the formula called again? I don't really have a name. I just know the name is you would be able to determine an areas like a ABC. You'll be able to determine a triangle's area using ABC over 4 times the radius of the circumcircle. So far, so good? Okay. Yeah. If all good, that's pretty much what I want to say for the first part. You know, there are so many formulas for you to determine the area of a triangle. It was like so easy for you to do the calculation, right? So if all good, let's go to our second category, try to remember some special angles trigonometry value. That's going to help you to save the problem, like save your time and expedite your calculation process. Let's go to our category number 2, knowing some special trigonometry. Okay, this guy, let's go for, oops, this guy, let's go for a problem. 2, oops, that's question. It's after certain raised. Yeah, that's the one. Very good. That's a problem that comes from 2016, from 2014, AMC10-A, question number 22. Again, give you some time to read it, and we're gonna see the answer all together. Yeah, by the way, student asking me why the previous question, the perpendicular line drawn from O to OB meet at the midpoint of the chord. That's actually using the isosceles triangle. Yes, so for the anomalous, your answer is using isosceles triangle. Isosceles triangle, the height is the same as the median of the bottom. So that's the reason why you have the perpendicular. Okay. All right, so let's have a look at for this problem. The problem says in rectangle ABCD, you have AB equals to 20, BC equals to 10. Let E be a point on the CD segment such that CBE equals to 15 degrees. With all those information, the question asks you, what's the value for AE? What's the value for AE? You know what? Again, if you go for the official solution for this problem, the official solution is going to be, do a lot of similarity, a lot of calculations, so on and so forth, and then figure out a value for the value of AE. However, like I said, if you can remember some certain values trigonometry, certain angles trigonometry value, you would be able to solve the problem in about 30 seconds. Why? Let's have a look at it. In order to determine AE, right? I think I need to determine the value for EC. EC is what? EC actually equals to 10 times tangent 15 degrees. Is it right? 10 is BC, right? I'm going to use that here, maybe BC times tangent 15 degrees, right? And do you know the value for tangent to 15 degrees? Let me just do a quick survey. Do you guys know the value for the tangent to 15 degrees? Have you learned this? Okay, so most of the students do not know this. Okay, so right, if you do not know this, then you have to do the complicated trigonometry similarity way. I mean, you have to do the complicated similarity way to get it work. However, if you know the value for tangent to 15 degrees, you can answer right away. I'm going to tell you this value. Tangent to 15 degrees actually equals to 2 minus under root 3. Okay, and later I'm going to give you a quick summary for this, but now you just remember 15 degrees tangent value is 2 minus under root 3. And what's the value for BC? BC is 10. So EC equals to 10 times 2 minus root 3. As long as you know this, what's the value for DE? DE is 20 minus EC, right? So DE is going to be 10 root 3. If you know the value for DE, what's the value for AE? AE is under root AD square plus DE square. AD is 10. It's a rectangular, right? So AD is 10. So AE, you can directly get answer, which is 20. So E is the correct answer. That's it. Like I said, you know some value, special angles, trigonometry value, you solve the problem in 30 seconds. But if you don't, you go to the LPS, you can check the official solution. That's going to take you forever. You got to do a lot of calculation to make it work. So that being said, in our regular lecture, we have already helped you guys summarize all the important values of the certain special triangles trigonometry. So please try to go back and check our notes. So those guys are very important. We actually help you guys summarize 15 degrees, 18 degrees, 36 degrees, 72 degrees, 75 degrees. These are very, very important. If you know this, that's going to help you to get your answer significantly faster. So for this problem, I'm going to write it one more time. What's the trigonometry value for 15 degrees? You need to remember this. This is very important. Sine 15 degrees is root 6 minus root 2 divided by 4. Cosine 15 degrees is root 6 plus root 2 divided by 4. And the tangent 15 degrees is 2 minus root 3. Okay? Like I said, we summarize all those values in our regular lecture. So these are also very important. But here, we just have to use this. Only the 15 degrees you'll be able to use in such a problem. Just like I said, it's kind of like a balancing, right? The more formula you know, the faster you can do the calculation. If you do not know this, of course, you can do the regular way, but that's going to take a lot more time. You know, this is question number 22. You're going to do a lot of calculations, right? So that's the reason why a lot of students keep saying they do not have enough time to do this AMC problem, because you know too less formula. The more formula you know, the faster you will do. In our case, if you know the value for tangent 15 degrees, you solve the problem in about 30 seconds. But if you don't, you're probably going to use maybe 5 to 10 minutes doing the complicated calculation to make it work. So far, so good? Any questions? All good? Okay, perfect. I think for the second category, it's very mechanical. One example is good enough. I just want you guys to remember special angles trigonometry value, right? There's nothing tricky. As long as you know it, you know it. You don't know it, then I'll just say good luck. You can do the calculation by yourself. Hopefully you get what you need. Okay, this is actually our second category. Sorry, this is our first lecture because we do a lot of warm-up introduction at the very beginning. We might do a little bit over time for today's lecture, but from our second lecture, we're going to be sharp for 2 hours. Okay, let's go to our third category. Our third category is actually using the circles tangent related problem. Okay, we're going to give you some problem. You're going to see some problem. They're talking about the tangency. As long as you know our conditional react, what we introduced in our lecture, is so easy for you to solve those problems. So one example, I think, is good enough. 3. Yep, that's the problem. We're looking at a problem that comes from 2016 AMC10-A, question number 21. Again, I give you 30 seconds. Read the problem first. Oh, oops. All right, so let's continue. Okay, this problem says circles with center PQR has a radius 1, 2, 3. Okay, 3 circles has different 3 radius, 1, 2, 3. Okay, they lie on the same side of the line and a tangent to L at P prime, Q prime, R prime. So basically 3 circles, they're all tangent to each other. And respectively, with Q is between P and R. So Q is in the middle, PR is on the 2 sides. The circle with the center Q is externally tangent to the other 2 circles. So the Q is in the middle, the other 2 is on the 2 sides. With all this information, the question asks you to determine the area of this triangle PQR. This is a weird triangle in the middle, right? I'm gonna make it smaller. You can say this is my triangle. It's kind of like a very slim triangle in the middle. This is my triangle here. I want you to determine the area of this slim triangle. Oh my God, this is not easy because this triangle is actually flying there, right? It doesn't touch anything. It's just like flying there. There's no way for me to determine a flying triangle's area. I must make sure the triangle, they can interact with something before I will be able to figure out what it is, right? This is something quite understandable. But before we go there, let's try to, like I said, before we jump to any kind of solutions, let's try to use some conditional react. In this problem, what are the conditional react I have to know before I jump to any kind of calculations? This is the different circles tangent to each other. Still remember? If you go back to C, we actually introduced, this is actually something very important. As long as you see different circles, they're tangent to each other, and you have a common tangent line, always remember there's a little magic triangle here, right? As long as you create this little magic triangle, you'll be able to solve the problem very quick, right? This is exactly what we introduced in our lecture. So let's have a look at it. Let's have a look at it. How are we going to deal for such a problem? Now I have a P and Q. These 2 triangles, each has radius 1. I'm going to change the color, radius 1, radius 2, right? You see, the question already helped you do a perpendicular line from P to P prime, Q to P prime. I'm going to do another line here, right? According to our definition, right? I would be able to determine the value for, let's say, I'm going to say this is H. H. Still remember what's the value for pH? pH is 2 root big R small r, which is 2 root 2. Is that right? See, this is our conditional react. Okay, let's do the second one. The second one is from Q all the way to here. I don't know, I'll give you a value, maybe Q. Maybe J. Okay, it doesn't matter, whatever value I want. Qj will be 2 big R small r 2 times 3 root 6. Okay. So that being said, your P prime R prime will be 2 root 2 plus 2 root 6, right? So this guy, I use the color green. This guy is going to be the blue one plus the red one. This is 2 root 2 plus 2 root 6. This is quite understandable, right? Now, how can I determine this red triangle? Like I said, this red triangle is flat. Now I finish up my conditional react, right? Everything is done. But how can I do this red triangle? This red triangle is actually flying there. It's not easy for you to determine the value of it, right? However, let's have some quick observation. This red triangle, I don't know how to do it, okay? However, I would be able to determine the area of this. I'm going to change color to here. Okay. I would be able to determine the area of my blue trapezoid, right? The blue trapezoid, P, Q, Q prime, P prime. This is easy, right? I know this is 1, this is 2, this is, you tell me 2 root 2. I can determine the blue trapezoid. Let's have a look at it. I can also determine this green trapezoid. Is it right? Exactly the same thing, right? Exactly the same thing. I have 2 here. I have 3 here. I have this is root 6 as the height. And my red triangle's area is just the blue trapezoid plus the green trapezoid and subtract my black trapezoid. Is that right? Do you agree with me? This is my black trapezoid. Black trapezoid, PR, R prime, P prime. Gonna write it here. My triangle's area will be my green trapezoid plus my yellow trapezoid minus my black trapezoid. Do you agree with me? Yes or no? Is it right? Because let's check it out. My blue one is PQ, P prime, Q prime. My yellow one is my RQ, Q prime, R prime. And my black one is this guy. You just basically use the black one plus you use the blue one, or use the green one. I think the color has been changed, right? Use the green one plus the yellow one, then subtract the black one. You will get the little triangle there, right? So easy. Like I said, these values are already given. 1 plus 2 times 2 root 2 divided by 2. 2 plus 3 times 2 root 6 divided by 2. This guy, 1 plus 3 times 2 root 2, 2 root 6 divided by 3. Basically, 1, 2, subtract 3, you get what you need. The answer is root 6 minus root 2. Easy peasy, right? Very understandable. You get what you need. Okay? So in today's assignment, I'm going to give you another sample, like another problem using exactly the conditional react. As long as you know the conditional react, it'll be so easy for you to solve the problem. Okay? So using what we introduced, how to do this is going to be extremely helpful. If all good, let's go to our last category. Okay? Our last category is kind of like some combination problem. You might see some PowerPoint, you might see some Ptolemy theory, so on and so forth. And this is considered to be relatively difficult problem. But trust me, most of the time, you know what? As long as you use a Ptolemy is always going to help you to do a lot of magic work. So let's go for one sample problem for it. Five. This is a problem that comes from 2016 AMC10-A, question number 24. Again, 30 seconds. Please read the problem. Okay, let's have a look at it. The problem says a quadrilateral is inscribed in a circle with a radius 200 root 2. Okay, the question already gave you the radius, 200 root 2. Okay, 3 of the sizes is, of 3 of the sizes of this quadrilateral has a length 200, 200, 200, 200. Now, the question asks you to determine the force of the side. To determine the force of the side. So that being said, you need to determine AD, right? What's the value for, as long as you get a value for AD, we're good to go. How can I determine the value of AD? Well, like I said, you already have a cyclic quadrilateral, right? The cyclic quadrilateral, you already know AB, CD, AB, BC, CD. The question asks you to determine AD. Of course, you have to determine AD. If a quadrilateral, you already know 3 sizes, the question asks you to determine the 4th one. So what kind of property you can really think about it? What kind of is there like a one formula help you to determine the value of it? Do you have one formula help me to determine the value of AD? Yes, I see student get the answer right away. Ptolemy. Ptolemy theorem says, as long as you know the 3 sizes, like 4 sizes, right? I'm going to just have to determine the value of AC or BD, right? A diagonal, and then we're good to go, right? You can either do AC or you can do BD because, due to the symmetric property, AC and BD are the same, right? Of course, AC equals to BD because this is a very symmetric property. So for now, all the problem becomes, how can I determine AC? Okay, let's have some quick discussion. How can I determine AC? As long as determine AC, BD is the same as AC, right? And then I use the Ptolemy. Ptolemy is AB times AD plus, Ptolemy is AB times CD plus BC times AD equals to AC times BD, which is AC squared, right? Because AC and BD are the same. It's a very symmetric shape. Who can tell me? How can I? Now I know AB, this is 200. CD, 200. BC, 200. AD is the question asked me to determine, right? The only thing is I need to determine AC. As long as I got AC, my work is done. Who can tell me how can I determine the value of AC? To determine AC, I'm going to give you a quick hint. I do a connection of AC, right? And I intersect the BO. BO is here, right? BO. Who can tell me these 2 lines, is there anything special? Or they just like random 2 lines intersecting each other? Who can tell me? I'm going to be asking Ryan. Ho? What is that?
And they're perpendicular because ABC is an isosceles triangle.
Is it right? That's a brilliant observation. this is perpendicular to each other. If this is perpendicular to each other, then AC actually equals to twice of EC. Is it right? If this is perpendicular, AC will be twice of EC. Because I just mentioned, right? As long as you got a chord is AC, right? And then from the circle center, you made a perpendicular line to the chord. You're going to cut the perpendicular line to two equal parts. This is what we introduced, conditional react. Every single problem, you should have this conditional react. If that's the case, if I can determine EC, then my work is done, right? I got EC, I got AC, I got AC, I got everything. How can I determine EC? Change the color blue. Is there something easy for me to determine EC? Who can tell me? Is there anything easy for me to determine EC?
Is it like a similar triangle?
Similar triangle, maybe not that much complicated. You can use one step to get it. Hint, using the area method. Who can tell me? Using the area method. We're gonna be asking maybe Michael Sun.
Is I think I can use the theorem's formula to find area of BOC, and then divide by BO divide by BO, and then multiply by 2 is multiply by 4 is the AC.
Is that right? That's a brilliant observation. Area method. Triangle, this black triangle, OBC. You know all the sizes, right? 200 root 2, 200 root 2, right? And then BC is 200. It's very easy for you to determine the area using Heron's formula. I'm going to write it here. Triangle BOC, you can use in the Heron's formula to determine the area, right? And as long as you got an area, you could be easily using 1 over 2 times EC times OB. OB is the R, right? And you can easily get a value of EC. Is that right? Like I said, area method is almost like every single geometry problem. So every single geometry problem, there was somewhat get some touch with the area method. So try to remember all the area method we introduced in our previous lecture. Our previous sections, our section number 1 is extremely important. As long as you got the area of OBC, so easy for you to get the value of EC. As long as you get EC times 2, you get AC. As long as you get AC, you plug it in, you get AD. It's very mechanical, right? Very straightforward. So trust me, there are so many solutions for this problem. If you check the AOPS, some solutions are very complicated. So I think this is actually a very straightforward solution. There's another even more straightforward solution I basically present to AMC12 class, because you're going to use the triple angle formulas trigonometry, which you do not have to know for AMC10. I think that's the number 1 straightforward solution. But for AMC10, I think using the Ptolemy theorem plus the Heron's formula is the most straightforward. There are way more complicated solutions. You can check it out from the AOPS website. All right, I think that's pretty much what I want to say for today's lecture. This is our lecture number 1. We only focus on the 2D geometry. There are a lot of concepts for the 2D geometry, but we consolidate them. We pick up the most important thing. So hopefully this 3, we start with the concepts, we go for the very important problem types, and then the representative of different types is going to give you an idea how you can deal with all those 2D geometry related problems. And hopefully you guys get a hang of it, understand the conditional react and all those important formulas you need to know in order to go to the AMC10 math competition. Yeah, that's pretty much for our today's open course. So from the next lecture, we're going to go to our regular lecture. Like our students, you can use the other link I sent you guys, and we can start our regular lecture. Open course is only for number 1. So hopefully you guys enjoy today's course, and today's course give you some hint, some idea for future math competition eventers. All right, that's pretty much what I want to say. Thank you, guys. I wish you guys a long weekend, and I wish you guys good luck. Bye, guys. Yeah, one more thing is if you want to have some free, I think we have some free courses. If you want to have like some free courses, you can scan this and ask your parents to, talk to the assistant. They'll be able to provide you some free lectures. All right, thank you, guys. That's pretty much for today's lecture. Bye, guys.